The idea of optimization is looking for the most or the least of something, making something as big or as small as possible. If you think about that idea, there's a lot of applications of this in the real world. If you run a business, what do you want to do? You want to make the most money you can. You want to maximize revenue. You want to maximize profit. One of the things that helps with that is spending as little as possible. So we want to minimize cost. If you make a product, you want to spend lots of money on the product that you're selling and not so much on things like packaging. So maybe we want to minimize the amount of packaging material that's used. Lots of applications. So we'll look at a general strategy for solving these types of problems. I'm going to throw a ball upward, and I have a function for height there. The goal is to find the maximum height. Now you may recognize this as something that you can do without calculus. My pre-calc class certainly has done problems like this semester, but the idea is to do it using calculus, and we'll certainly encounter other problems that we wouldn't be able to approach except by using calculus techniques. I wish I could talk. So let's look at a general strategy. First thing I want to do, make sure you know where you're headed. What's the problem asking? What are we trying to do? Something that helps with that often is draw a picture and label it. Things are just easier to talk about when they have names. I'm going to throw a ball upward, so it's height above the ground after t seconds. So it's going to start somewhere, it's going to go up, it's going to turn around, and it's going to land on the ground. That's my ball. The picture is not particularly helpful in this particular case, but we have a good understanding of the problem now. Now I want to make sure I know what function I'm trying to maximize or minimize. This is the best case scenario right here because we have it. It's given explicitly. Here's the function for height above the ground, and I want to maximize it. That won't always be true. Sometimes we'll have to come up with a function. Maybe it'll be a formula that you know from geometry, similar to what we did when we were talking about related rates. Something that comes about because of the picture that we drew. But this time, we know the function. Next, we get one variable to work with. So if the function that you come up with has more than one variable in it, we're going to need to make some substitutions so that we have the function in terms of one variable only. Sometimes there will be a constraint, another piece of information about the situation that'll allow us to make these substitutions. But we're looking for one variable only. Here we're just throwing a ball in the air. We don't have any constraints. You knew this part was coming. If I want to maximize something or minimize something, I'm going to need critical numbers. And to find those, I'm going to need to take a derivative. So once we have the function figured out and we have it all nice in terms of one variable, we'll take its derivative. Set it equal to 0, look where it doesn't exist. Find the critical numbers. Maybe that a maximum or minimum occurs at an endpoint of the reasonable interval for the function. Thinking about this one in particular, I'm starting with a ball. I'm going to notice h of 0 is 200. So maybe I'm standing on a cliff or something. My ball is starting 200 feet above the ground, and it's going up from there. And eventually it's going to land back on the ground so that its height above the ground is 0. So whatever the maximum is, it's not going to occur at the end. The maximum height above the ground is not going to occur after the ball has fallen on the ground. And the maximum also doesn't occur at t equals 0 at the beginning because I'm throwing the ball upward from there. So we've considered endpoints. Those don't make sense in the context of this problem, so I'm just going to take my derivative. Here we go. So I got negative 32t plus 192. And I'm going to set that equal to 0 to find critical numbers. Subtract 192, divide by negative 32, and I get t is 6. So that's lovely. T is 6. Have we answered the question? The question was, find the maximum height. And I have t equals 6. So I have not answered the question yet. I've found when the maximum height happens. It's going to happen 6 seconds after we throw the ball upward. But what is the maximum height? We're going to need the function for that. So h of 6. And when all the dust settles, we get 776 feet above the ground is the maximum height. It may be that we want to check and make sure this is really a maximum. For this particular one, we drew our little picture in the beginning. That's definitely where the maximum happens. But if we need to, we can check that we've actually found what we were looking for with the second derivative test is a pretty efficient way to do that. So even though we're pretty sure that this is a maximum, we'll go ahead and take another derivative. Second derivative is negative 32, which is negative no matter what. No t's in there to be found. Second derivative is negative, which means we're concave down at t equals 6 and everywhere else, which means this is in fact a maximum. So that's our general process for solving optimization problems.